Okay, welcome back. Uh, Derivatives of inverses. We're looking at 3 point something, 3.6. Move the paper down a little bit. Okay, um, basically, if a function is continuous and f has to have an inverse, obviously. In that case, it's if f is continuous, its inverse is also continuous. So this is stated in theorem 3.16. It's proven in the book. Geometrically, so if f is continuous, then f inverse is continuous. Geometrically, this makes sense because if you remember sort of your construction of an inverse function, so let's take something that's continuous and is invertible. So if it's one-to-one, it's invertible. So that really puts a lot of constraint on what kind of thing you are working with. But to construct the inverse given a function that's invertible, all you have to do is rotate it about this line y equals x. Right? And in doing that, this rotation, you don't expect any holes to magically appear. So at least, hopefully, geometrically, that's kind of convincing that if f is continuous, then f inverse will also be continuous. If f has no holes in it, then f inverse won't have any holes in it. Likewise, you can think of derivatives in this kind of way. So we'll end up having f is differentiable. If f is differentiable, then f inverse will be differentiable, sort of. Okay. So intuitively, what is the derivative of f? Well, that's a function that tells you the slope of the tangent line at any given point on the graph. And so it makes sense that if this thing, and let's again do this kind of rotation, if this thing has a tangent line on this curve here, then you would expect that this thing has kind of a tangent line on this. Right? It'll turn out that the slopes at these 2 points are reciprocals of each other. And I don't know. Basically, this will work. If this thing has a slope of a tangent line here, this will have a slope of a tangent line here for all cases except when the derivative is 0, because if you're thinking about reciprocals, the reciprocal of 0 is undefined. So if we do, in fact, have a horizontal tangent line on f, then that will not allow us to be able to find the derivative of the inverse function. So this will be true so long as f prime at a particular point is not equal to 0. Okay. We can sort of get a formula for the derivative of the inverse function, and it's given in theorem 3.17. But you can get it, you can generate it by doing kind of this implicit differentiation thing that we learned in the last sections. So consider then the following composition. F how do we want to do this? So f of f inverse of x. And if you do this composition with inverse functions, if you remember, you end up just getting x right back. Okay, so okay, so we have this expression. I want to take the derivative of this thing, and so I'll have f prime of f inverse of x, and then you just multiply it by the derivative of the guts here. So that's going to be what we're kind of looking for. We want to know the derivative of f inverse. Okay. On the right-hand side, the derivative of x is 1. So we can solve for the derivative of f inverse just by dividing both sides of it by this portion here. So you get f inverse prime of x is equal to 1 all over f prime of f inverse of x. And again, it's kind of suggests this idea, you know, if f prime of something is equal to 0, then this thing is not going to be defined. So there's this sort of issue that you see in the formula that we've created for figuring out the formula for the derivative of f inverse. Okay, so this will be the formula for the derivative, you know, so long as this thing is not 0. Okay, so anyways, moving on then. Let's look at some of the questions in the book. In particular, here's number 3. Verify f has an inverse, then use the information to find f inverse prime of a. So 3, we have f of x equaling x cubed plus 2x minus 1, and a is given as 2. So first we want to show it's invertible, and it's not entirely clear this thing is invertible. We want to show it's 1-to-1. There's sort of algebraic ways to do that. So you say, supposing f of x1 equals f of x2, you should basically have to show x1 is equal to x2. Algebraically, I don't see that happening for us. So what we're going to do is probably go to the derivative and just show it's always increasing. Show the function's always increasing or decreasing, and that'll do it. So f prime of x is equal to 3x squared plus 2. Okay. This thing is always going to be greater than 0. Okay. So if you plug anything in for x squared, it's going to be greater than or equal to 0. And then when you increase it by 2, it'll definitely be just plain old greater than 0. So this implies that the function is increasing. And that implies it's 1-to-1. Okay. And supposing a function is 1-to-1, then you could say it's invertible. Okay, so we're good there. Next step, part B, we want to evaluate the derivative of the inverse function at this point a equals 2. We don't actually know the inverse function, okay? And it's not entirely clear to me how I would solve for x if I had set this y equals x cubed plus 2x minus 1 and then replace the variables. So yeah, x equals y cubed plus 2y minus 1. How would I solve for y in that case? I don't know, but we could still find the derivative, get a formula for the derivative of the inverse and use it to kind of figure out particular values. Okay, so it's not going to be 100%, but we'll get something, right? So recall then for our formula of the derivative of the inverse, that'll be 1 all over f prime of f inverse of, in this case, we're concerned about the number 2. Okay? So in particular, then, we need to find if this thing is y equals x cubed plus 2x minus 1, this is actually asking for what value x is y equal to 2. Okay, so that's the question this thing asks. F inverse is some function of y in a way. If I solve this out for x, it would end up being a function of y. So you're plugging 2 in for y, right? So you'd have 2 is x cubed plus 2x minus 1, and then you would solve for x, and that would tell you this value, okay? Like I said, we're probably not going to be able to solve for x here, so what we do is just kind of guess. You put 1 in here, and what do you get? So 1 cubed plus 2 minus 1. 3 minus 1 is 2. Oh, I got lucky, right? So that tells me f inverse of 2 is equal to 1. Okay. I know what y prime is, or f prime. That I got that from part A. It's 3x squared plus 2. So I can kind of figure this out now. It's 1 all over f inverse of 2 plugged into f prime. Okay, so it'd be 3 times 1 squared plus 2, which is 1 all over 5. Okay. Note that the derivative of f, and I shouldn't have wrote f inverse prime of x. I should write f inverse prime of 2, right? This is probably hard to read. So what is this thing? It's f inverse prime of 2 is equal to this thing. Just really quick, let's look at f prime of 1, which will be 3 times 1 squared plus 2. And of course you get 5, which is the reciprocal of this thing, which is what I was saying, that the derivatives will be reciprocals of each other. Okay, let's look at another issue. So from, I mean, we already kind of figured out some, so if you have y equals e to the x, we know y prime is e to the x. The question kind of was answered earlier. The derivative of the inverse of e to the x is, what was the inverse of e to the x? So the inverse of e to the x is ln of x, and then its derivative is 1 over x. Okay? And we were kind of able to finagle this answer by working with this expression. Okay? We want to do this construction for all of the inverse trig functions. Right? Okay, so derivatives of inverse trig functions. And there's going to be two main ones that we worry about throughout calculus: the inverse of sine, and then the inverse of tangent. Okay. Okay, so if in example 3, we're worried about the inverse of tangent. Let's just remind ourselves what tangent looks like. Okay, so tangent has asymptotes at negative pi over 2 and pi over 2. Etc. An infinite number of asymptotes. So this is y equals tan of x. And the asymptotes happen whenever you have cosine equaling 0, because tan of x is really just sine of x all over cosine of x. So whenever cosine is 0, and of course you can think of the unit circle, cosine is always 0 at like pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. You're going to see these asymptotes popping up at those places. Right? All right. First off, this thing is not invertible on its whole domain, and that's obvious if you do the horizontal line test. It hits the graph in more than one place. So what they do in order to make it invertible is to restrict the domain. and we'll restrict it to negative pi over 2 to pi over 2. And when you do that, then it becomes invertible, and the inverse kind of looks like this. Looks like a cube root function, except it has asymptotes. Right? So it has asymptotes there at pi over 2 and negative pi over 2. So this is y equals tan inverse of x. Right? One issue that always comes up later on, I don't know if we even want to go there, but we'll talk about infinite limits eventually, so you might as well start talking about it now. The limit as x goes to infinity in this direction, where are the y values going? Well, they're going to level off to the asymptote, which would be pi over 2. So limit as x goes to the infinity, that'll be pi over 2. The limit as x goes to the negative infinity of tan inverse of x will equal negative pi over 2. So you go in this direction, we're coming down like that, negative pi over 2. Okay. So anyways, we need to figure out a formula for the derivative of tan inverse. And we could work with this new formula for the derivatives of inverse functions. So in particular, the book wants you to find the derivative of y equaling tan inverse of x. Okay. So first what we're going to do is kind of note the following. If you have tan inverse of, I don't know, we'll say x equaling y, which is kind of where we started, right? We could take the tan on both sides. So this would be tan of tan inverse of x equals tan of y on this side and this side. We could, I guess we could take derivatives, right? So cat please. So it seems like I'm getting in trouble. I mean, this side is equal to x, so it's really tan of y equals x. If you do the cancellation equations on this thing, and then let's take the derivative implicitly here, I guess. So you end up with secant squared y times y prime equals 1. Okay. So what is y prime? Well, that's what we're looking for, right? We want to find the derivative of y, and y is tan inverse. So we could solve for this. So, you know, you get y prime equals 1 all over secant squared y. You could use Pythagorean identities to solve for this. So probably the book uses triangles. What is this thing? Well, y prime is 1 all over secant of y, and secant y is tan inverse of x, right? And then this thing is squared. So let's turn that into a triangle here. So tan inverse is this angle here, and remember tan is opposite over adjacent, so it's x1, and then we get the square root of, using Pythagorean theorem, x squared plus 1. Okay. So the secant of this angle here, the secant is 1 over cosine, so that's going to be hypotenuse over adjacent. I could replace the secant of tan inverse of x with square root x squared plus 1 all over 1. Okay. So let's do that, and we'll have a nice algebraic type formula for the derivative. So what did I just say? So y prime is 1 all over, using the triangle now, the secant of this angle is hypotenuse over adjacent, so I can replace secant of that angle with hypotenuse x squared plus 1 all over adjacent, which is just 1, and of course we're squaring this, and then supposing we square it, we just end up with 1 over x squared plus 1, and that's the derivative of the tan inverse function that we were after. Right. Okay, so that's one of the important ones. In general, then the two main important ones, the derivative with respect to x of sine inverse, and we'll put it in general terms of u, that'll equal 1 all over the square root of 1 minus u squared times whatever the derivative of u is with respect to x. And then the derivative with respect to x of tan inverse of u, what is that? That'll be 1 all over 1 plus u squared times the derivative of u with respect to x. And then, so these are the ones you got to have memorized, okay? People memorize. They come up again and again, and your familiarity will help you get your homework done a lot faster, okay? So, and do well on tests, obviously. But these are the ones you want to have memorized. This last guy doesn't come up very much, so you want it sitting around in case you see its form in a homework problem or something like that. Arc secant, it should be secant inverse. I don't know why it's the way I wrote it in my notes. That'll be 1 all over absolute value of u times the square root of u squared minus 1 times, again, the derivative of u with respect to x. Obviously, you know, this one's a little more complicated anyways, so, you know. Okay, so let's actually find the derivative of some of these characters. 25, we have g of x equaling 3 arc cosine of x over 2. Okay, so g prime of x, leave 3 alone, so we have 3, and then the derivative of this, where our u is the x over 2 in this case. So I didn't include the arc cosine formula up here, but it's just the negative of sine inverse. Okay, so this answer, if this was cosine inverse, this would be negative of this. Okay, so if you know the sine inverse, then the cosine inverse is just slapping a negative. All right, so we have 3 times negative 1 all over square root of 1 minus u squared. So our u squared is x all over 2 squared now. And then times the derivative of the x over 2 part. So the x over 2 is 1/2. In general, when you're doing simplifications, you want to get rid of complex fractions. So what do we have? Negative 3 all over 2 square root of this thing. You know, we have a 1 all over x all over 3. You want to avoid those. So we want to rewrite this as it sits. X all over 2 squared is x squared all over 4, right? So if I factor out a 1/4 from this expression, I'll have 1/4 times 4 minus x squared, okay? And then I can take the square root of 1/4 and I get 1/2, so it'd be negative 3 all over 2 times 1/2 is just 1. So at the end of the day, we get square root 4 minus x squared. Okay. Let's keep moving. Number 31, we have g of x equaling e to the 2x sine inverse of x. Okay? So this one requires a product rule. So g prime of x equals, leave e to the 2x alone and take the derivative of this. So it's times 1 all over the square root of 1 minus x squared plus leave sine inverse alone, take the derivative of e to the 2x. So the derivative of e to the 2x is just e to the 2x, but then times 2. You take the derivative of the guts, and then times leave sine inverse alone. Not much you can do in the lines of simplification here. So we'll just rewrite it a little bit to make it a little more obvious. And there we go. Okay, so it looks a little prettier. Let's look at 35. So I have h of t equaling sine of arc cosine of t. whenever you have a composite where one function is an inverse and the other one's not an inverse, you can use the triangles to simplify these. Okay, so in particular, then arc cosine of t will be this angle. Cosine is adjacent all over hypotenuse, so you just pretend t is the same as t over 1. And then as a ratio of sides of a right triangle, cosine is adjacent over hypotenuse. So it must be t for adjacent, and then hypotenuse is 1. The third side you get using the Pythagorean theorem, so the third side would have been 1 minus t squared. Okay, so the sine of this angle in particular is opposite over hypotenuse, so I can rewrite this as 1 minus t squared, all over 1, but we don't write that, right? Okay, so find the derivative. H prime of t will be, bring down the exponent, so you know, if you need to, you could rewrite this as 1 minus t squared, the 1/2. Bring down the 1/2, you get 1 minus t squared to the negative 1/2, and then times the derivative of the guts, negative 2t, and then clean it up a bit. So 1/2 times negative 2 is negative. We have a t up there. Drop this guy into the denominator, 1 minus t squared, and I'm just going to rewrite it with a nice square root there. Okay. Okay, let's just look at maybe one or two here, random problem, maybe just one random problem. Let's look at 49. They want you to find the equation of the tangent line to the curve. So 49, we're given y equals 2 sine inverse of x, and the point is 1/2 comma pi over 3. Okay. Alrighty then, so y prime is 2 times the derivative of sine inverse, which is the square root of 1 minus x squared. Right, and then I want to evaluate this derivative at 1/2. So y prime of 1/2 is going to be 2 all over 1 minus 1/2 squared is 1/4. Okay, so that's going to be 2 all over the square root of 3/4, which is 2 all over square root 3 all over 2, which is 2 times the reciprocal of the denominator, which is 4 over root 3. Probably want to rationalize the denominator just out of respect for our forefathers. We have 4 root 3 all over 3. Okay, so that'll be the slope of the tangent line at that point. Then we need our point slope formula. Y minus y1 is m times x minus x1. And we're just plopping in information. Here's our point, here's our slope. So y minus pi over 3 equals 4 root 3 over 3 times x minus 1/2. And then hopefully clean that up a bit. So you get y equals 4 root 3 over 3x minus 4/3 times 1/2 is 2/3, so you end up with 2/3 root 3. And then add the pi over to have a nice form going on there. Yeah, so that's pretty much it. You get really carried away with all the technical aspects of the you know, these concepts of inverses, and you know, is the thing continuous? I encourage you to read the proofs in the book. Okay, thanks a lot.